Okay, welcome everyone to this week's CDAC talk. Today I'm pleased to introduce Dan Sun from the National High Magnetic Field Laboratory at Los Alamos. Our second talk in this series from the LANL Maglab. A little bit about Dan's background. She obtained her PhD from the University of Toronto in 2014, then took a postdoc position at the Max Planck Institute for Chemical Physics before moving to Los Alamos as a postdoc in 2018. Her research interests include high field and high pressure studies of semi-metals as well as high temperature hydride superconductors, including recent work on the very high TC lanthanum hydride system that was discovered by our group in CDAC a couple of years ago. So thank you for joining us, Dan, and we're looking forward to your talk.
Yeah. I'll enlarge this into a full screen mode. Hey, hello everyone across the internet. And as Russ just introduced, I'm a postdoc in Los Alamos National Laboratory. And yeah, I want to thank Blake for recommending me to this talk series. And I want to especially thank Russ for organizing this nice workshop series, because we really exchanged a lot of emails since the beginning of October. So today I will bring you the our high pressure, high magnetic field research here at Los Alamos Maglab. And the highlight would be a recent study of hydride superconductors. This is a collaboration between many institutes. And I think my mentor, Feder, is also in the audience. Natalia also see him. Yeah, hello, everybody. So I have so much to share with you in my talk. So this is a table of contents. I will first introduce a high magnetic field facility that's a Maglab. And then I also want to show our design of a pressure cell for pulse magnets. Then I will show you the high magnetic field measurement of lanthanum H10, which is a hydride superconductor. And if time allows, I also want to share another recent research on the H2S. It's another hydride superconductor at high magnetic fields. So we start with introducing the study of extreme field studies. We stay on the Earth. We have a magnetic field about half Gauss naturally, but that's rarely enough for research in electron systems. So usually when you get a cooling system, for example, a PPMS system, they would provide you with a 6 Tesla, 9 Tesla, even 12 Tesla of magnetic field. But if you aim for something higher, say tens of Teslas, usually the normal magnets, the normal labs cannot provide that kind of high magnetic field. In this case, you have to go to facilities that has expertise on the extreme field. And depending on which range of field you need, different technologies is available. If you want to keep your magnetic field in a time extent of hours, we call that DC magnetic system. For the most powerful DC magnet system can provide you with 45 Tesla magnet. But if you want to get higher field, that field cannot last that long. Usually it's showed with a pulse form, which means you reach high magnetic field, but only in a split of a second. And with that, usually you have to store an amount of energy, and suddenly you release the energy and have a big pulse. That is usually realized in a motor generator or capacitor bank. That would provide you to about 100 Tesla. If you need even higher, that is also almost always like supported with explosion, which means you have a high field already, and then you physically explode your system and shrink the physical volume so that the flux of the magnetic flux can be squeezed reaching a higher magnetic field intensity. So, and through this description, you can understand that the higher the field, the shorter time you are allowed to get this high field. So this plots the magnetic field intensity with the time duration you can get from different systems. So here in US, we have a national Maglab. It's a user facility. It extends to different campuses. In Florida State University, they can generate 35 Tesla with a purely resistive coil called Florida Beta magnet, and with a hybrid magnet, which means they connect the resistive wire together with superconducting wire that can provide a DC field of 45 Tesla. That is their record-keeping field. And in University of Florida, they achieve the record in a different way. They have a very powerful fridge that can keep the keep cool at 1 millikelvin for 6 weeks. So together with 7 Tesla magnets, they have the highest B/T facility. And here in the mountains, we have a pulse magnet facility, and we are here in Los Alamos in New Mexico, and we have a record of 100 Tesla pulse magnet. And to provide the energy for this magnet, we use a motor generator as big as this, compared with a human being here. So a little bit more about the Maglab at Los Alamos National Lab, LANL. We have an international user program here. In the normal years, we have 150 to 200 visiting scientists each year, and 20 of them are from overseas. The record fields of this facility is 100.7 Tesla, but that is for the normal years. This year, due to the COVID situation, we stopped allow users onto campus since the beginning of the year, March or April. And now we have a remote user system, which means the users mail the sample to us, and the scientists here will measure the samples for them without taking the risk of traveling through places. So this is a photo. The left one is a photo showing the magnetic cells available to users. And in each of them, there's a 65 Tesla magnet installed. In the normal days, out of the 4 magnetic cells, 2 or 3 are used for each week to provide users with 10 pulses per day. And here is another photo. Because the photo policy here in LANL is pretty strict, so I have to use some old photos, which can be shown by those big monitors you are using. But other than that, the cell still keeps the same. We provide high quality of field environment, and we have high impact publications each year. So then there are different technologies as introduced before. In Tallahassee, we have 45 Tesla DC field, and in Los Alamos, we have 65 Tesla non-destructive pulses, and our proud record of 100 Tesla non-destructive pulses here. And if you want more, Los Alamos have this single-turn technology, enable you to get the field to 150 to 300 Tesla. So the coil will be melted after the pulse, but with a larger chance, your sample would be still kept, but we don't call it multi-shot. So later in this talk, I would especially introduce the 3 systems: the 45 Tesla DC, 65 Tesla pulse, and 100 Tesla pulse. We use the 45 Tesla and 65 Tesla magnet to do our hydride research. So first comes with this 45 Tesla hybrid magnets. it's a huge one, expand to the room of 2 floors. So by meaning hybrid, it means they use both superconducting coil and the resistive coil to provide this big field. Shown by the the red-brown part, those are the superconducting magnet. With this part, they provide a constant 11 Tesla magnetic field, and in the inside, after some in the inside, they have some resistive coil that provides further 34 Tesla. Add up, we can have 45 Tesla DC that's provided to the users. Because the central coil is resistive, it needs a lot of cooling power to take out the heat generated during the DC pulse. And you can see here, there are huge cooling power pipes going through. And the coil is a little bit different than we think of the normal, very traditional transformer coils. It's actually made by connecting plates. In the middle one, the middle plates, they have elongated holes to maximize the hoop strength. And at the end, the holes are ellipse, so that they can increase the bending stiffness. And then connecting them all together, the water actually flows through the holes of those, providing enough cooling power. So this is a gigantic magnet, and we use this to study our lanthanum hydride project. And here in Los Alamos, we have 65 Tesla pulse magnet. And the central figure here shows a cartoon of the composition of the magnet. There's a capacitor bank, and it accumulates energy. When the switch is pulling down, a surge of current is feeding into the coils, providing this kind of pulse. And this shows the time profile of the magnetic field. You can see that the field first arrives quite quickly and then drop down kind of slower. This whole pulse would last about 30 microseconds, depending on how you define the width of the pulse. And so usually we have maximum field of 65 Tesla, and we usually run it to 60 just to make the coil run a little bit longer. And for each of the pulses, we need 45 minutes to cool down. So if people usually work 8 hours, and that probably provide you 10 pulses up to 60 Tesla. And inside the energy release during the pulse is about 1 millijoule, and that's actually a stick of a chocolate bar. I mean, that doesn't have much of the energy, but here we use a capacitor bank as big as probably my whole apartment. So that's how much of the thing you use to contain 1 millijoule, 1 megajoule of the energy. And here, this is a photo of our magnet system. The upper is the sample probe. You can just visualize it's a stick that sticks your sample into the field environment, and your measuring probe, like wires and cables, they come out through the probe connecting to the measurement instrument. And then lower, this is helium-3 cryostats. This one provides you to low temperatures as low as 500 millikelvin. In a good day, it even reach 400 also. And down there, it's a magnet. And now you notice around the magnet, there's a black box. Why is that? Because actually those magnets is limited by the strength of materials, and they will fail. They have a limit lifetime. After about 100 or 500 pulses, they will die and then they will explode. So the strong magnets generate big pulses, and to have a 80 Tesla pulse in the Maglab magnets, it usually generates a radial pressure about 1.4 GPa. So we have a lot of high pressure experts here in the audience. We work with hard materials. We know that for most of the material, it just cannot handle this kind of pressure. And this is a big facility. We just cannot use diamond everywhere. So we use the world's strongest conductor and strongest steel. And each pulse, it will apply the pressure that high on the radially. After a lot of repetitions, this would explode, and it will suddenly explode. But understand that actually the pulse, the field, the upper limit field is limited by the strength of the materials. The technologists and engineers work hard to push this limit higher and higher. And here we have this 100 Tesla multi-shot magnet. In the middle, this is the cartoon drawing of our 100 Tesla magnet. In designing and materials, we use hard conductors, copper, niobium, and we use MP35N sheet to reinforce them. And also on the side, we use nylon fibers to further enforce them. The inner coil here has a 15 millimeter bore. It provides 55 Tesla. And for the outer bore shown here, it provides another 47 Tesla. It has a 220 millimeter bore. These magnets, they use even higher energy. And for the outer coil, we have 125 megajoule. And that is provided by the motor generator I showed you before. So this is the time profile of this pulse. You can see that we have about 1 millisecond at 100 Tesla peak field, and we have about 10 milliseconds above 75 Tesla. The whole duration, the pulse duration lasts about 2 seconds. And the specification of this magnet is we have 100 Tesla peak field, and the bore is 15 millimeter. With this, we still have to fit in a refrigerator if you need a low temperature. And with this, we can have pulse every hour. And this is 1 meter, and you can see the scale of this big magnet. So we actually get a lot higher in field, but there are something you have to take. So there are some disadvantage you have to take to get this high field. As the time profile shows, the field change real rapidly through a very short time. And usually when you change magnetic field quickly enough, it will introduce eddy current. And this photo shows the real eddy current in the liquid. And so which means if you have conductors in this rapid changing field, you will have severe heating in the cryogenic systems. At liquid helium temperature, this can be as high as tens of kelvins. That would, for one thing, change your measurement temperature for your environment, and for the other thing, exert a lot of danger on the system. And we know that this generated power is proportional to the square of dB dt and the area that's perpendicular with the field. dB dt is something we cannot change, so to avoid heating, we just avoid to use any metal. So here comes another topic. The demand for combining very high magnetic fields and high pressure is always high. And I was trained as a pressure expert since my PhD years. I would say we should work on that so that we can combine the high pressure with high field. However, those new technologies always comes with challenges. The first one is limited space. As I introduced you before, the field is limited by the strength of the materials. So to wind the coil, the final left sample space for us is very limited. And because of this eddy current, we don't want to use metal. we want to, there will be heating with metals. So we want to avoid metal as far as possible. As we have a lot of pressure experts here in the audience, we know for the conventional pressure cell, usually we use hard metals to provide the strength, and usually they are not small enough for the limited space. So we have we design our pressure cell that is aimed to be used in magnets in low temperatures. It is a diamond anvil cell. It's mainly made of G11. This is epoxy embedded fiberglass. So this can largely avoid heating. However, we want to lock the pressure cell with some mechanism. We need thread. Although the G11 is very hard because it's a epoxy embedded glass fiber, it's not suitable for threading. So we have to use some metal. Here we use titanium screws and end plate. This long titanium screws first act as a locking mechanism and also act as the alignment mechanism to fix the cell. And here is a photo of the pressure cell. It has a diameter of about 9 millimeters, and they are just squeezed by the screws, and it has a thread on the bottom end plate to lock the pressure. And in between the bodies, the anvil sits, there are 2 diamond anvils. We actually use both left and right hand screws so that when locking the pressure cell, we can use both hands to lock them evenly. And with all those designs, this pressure cell can reach to a pressure up to 7.5 GPa, and it holds for days or weeks. So there's another complications. There's a gasket. Usually the gasket is made of metals too. However, the gasket is one of the material that's most near to your sample, and it has a large area perpendicular with the field. So we don't want to use any metal gasket. We read this paper that they use boron gasket designed for X-ray measurement. We make our gasket out of boron powder embedded with epoxies, and we use a further layer of captain to provide the strength radially. For the metal part, we cannot avoid, that is titanium end plates. We did modeling and we cut the patterns to reduce the eddy current, like so. In the modeling, we can see that after cutting the thread, the slits here, the eddy current is hugely reduced. Also, for better measurement of pressure, we use 3D printing technology to make a probe top so that we can feed optical fiber to the vacuum system. And with the help of another portable spectrometer station, we can measure pressure at low temperature just before the pulse so that we can get the pressure as accurate as possible. Here is some exemplary spectrums for the pressure we did. Both in room temperature and 4 Kelvin, the pressure cell can hold 74.5 GPa and for a long time. So also, we are concerned of the heating. We measure the heating during the pulse. We found that for magnetic field up to 65 Tesla and with the temperature down to 500 millikelvin, no noticeable heating is generated during the pulse. Furthermore, we calculated the length ratio of the plastic body and the screw so that the thermal contraction can cancel each other. Turns out, when cooling from room temperature to a low temperature, the pressure changes within 10%. And yeah, this result has been recently placed onto arXiv. So if anybody is interested into the high pressure, high field research, please check for that. This pressure cell has been used into a recent measurement. It is a proximity detector oscillator, and shown by this figure, the sample itself is a powder sample, and there's a coil placed in the middle. The coil has a diameter of 125 micron, and they are made of gauge 58 copper wire. That is 9.910 micron wires, and it has 3 turns. So here is a photo through the microscope through the diamond, and it is under high pressure. You can see that the coil keeps the shape under pressure, so that it can just reliably collect the signal. Those are the exampling data from the measurement. To understand those data quickly, the change in frequency is proportional to the magnetization of the sample. With this measurement, we can study the magnetization behavior of the sample at different pressures at high field. So, but sometimes the challenge comes with different ways. And now here I would turn to the new topic, the high TC hydride superconductors. I know there in my audience, there will be a lot of experts on the hydride research. So I would keep the introduction short and brief. So by BCS theory, if a superconductor is mediated by the lattice, the later the lattice, the higher the TC. So this places hydrogen into the natural candidate of a superconductor with the highest TC. But the drawback is to place, so in the ambient environment, hydrogen usually stay in the dimer molecular form. One need the really high pressure to make the hydrogen into a metallic form. This pressure is stayed as high as 500 GPa. So this was always a challenge for the high pressure community. To reduce the pressure, people find that some heavier atoms, when placed in, they can chemically pre-compress the system. Thus, lower pressure is needed to achieve superconductivity in hydrogen-rich compound, which we call it hydride. H3S is the first high TC hydride superconductor achieved recently, which had a TC of 200 Kelvin. And then later, lanthanum H10 is another good candidate. It has a TC of 250 or 260 Kelvin. That hugely raised the record about 50 Kelvin. And just recently, a few months ago, a hydride containing sulfur and carbon is made with a TC of 288 Kelvin. That realized the long pursued room temperature superconductor. So a few words about lanthanum H10. In lanthanum H10, the lanthanum atoms act as nucleation centers, and hydrogen forms cage-like structure around them. The lower right corner shows a plot of the crystal structure from the following paper. And what's more, the distance between hydrogen atoms is close to what predicted for atomic metallic hydrogen, near 500 GPa. So with this high hydrogen content and with this similar hydrogen distance, we can actually regard lanthanum H10 as doped metallic hydrogen. This is one of the original research shows the superconducting phase. So for one thing, it shows us a sharp transition at 250, and you can see that when it is in a superconducting state, the resistance really reached to 0. So now we know TC is high and the energy gap would be high. We have to use high magnetic fields to prove this system. With a lower field measurement up to 9 Tesla, the extrapolation of HC2s is extracted to about 100 Tesla. So we have to use those high field facilities to research in them. And we also know that the sample itself is a pressure cell. We don't want to destroy them. the one that is left for our choice is this 45 Tesla system in Tallahassee and this 655 Tesla in Los Alamos. So here is a few words about our samples. The lanthanum H10 is directly synthesized from lanthanum and hydrogen inside a diamond alloy cell, and later they are heated by laser and to finish the reaction. After the reaction is finished, the sample has a lateral dimension about 10 to 20 micron and has a thickness about 2 micrometer. And this one shows a photo of the sample through the microscope. And we also deposit deposit leads on the diamond. It has a van der Waals configuration that enable us to measure transport properties like resistance and Hall effect. As I introduced, for those high field facilities, the sample space is usually very limited. So a miniature CDAC is designed for this kind of measurement. It has a maximum diameter of 8.8 millimeter and have a length of about 30 millimeter. This photo shows the pressure cell mount onto a DC magnet probe, and compare with my finger, you can see that it's a small one. So to do this experiment, we get a list of pressures. And for each of the pressures, we measure the temperature dependence of the resistance. For one thing, we can see the transitions are sharp in the temperature. And I also zoomed out near the zero by 3 orders. So this is 3 orders smaller than the previous one. You can see that in the superconducting phase, it really reached 0 within the measurement errors. And then I plot TC against the pressure. We can see that the TC increased quite a lot through a narrow pressure range. So we think this behavior is quite interesting. We want to understand the mechanism behind it. So we choose 2 samples, one at 120 GPa here, and one at 135 GPa, 136 GPa here. Also, we found the TC versus pressure relation can be reversible, which means if a pressure cell lower the pressure, if you relax the cell to the same pressure, the TC can be kept the same. Now we choose the 2 samples. Before we place them into the magnetic field, we measure the temperature dependence of resistance at 0 field. They show like this. So for both of the material sample in the normal state, the temperature dependence is pretty linear. And for the 120 GPa sample, the transition is narrow. For the 136 sample, it's wider, yet it has a kink at the transition. Through all those data we get, we can calculate for the resistivity. It's about 0.3, 0.4 milliohm centimeter, and the large error comes from the estimation of the thickness of the sample. And then we place the 2 samples into the high magnetic field. The left one shows the sample at 120 GPa. It was measured in the DC magnetic field, and which you can see that the highest field goes to 45 Tesla, and some of them stop at 11 Tesla. Just as said, we keep the superconducting coil at 11 Tesla, and we change the temperature and ramp the field up and down. So the other thing you can notice is the transitions are wide in the magnetic field, because when there's magnetic field, there will be appearance of vortices, and that would intrinsically widen the curves. And also their inhomogeneities of the samples makes the transition even wider. Because it is wide, we want to characterize all the widths of the different critical field. we define the upper critical field HC2 as a field where the slope of the normal field and the slope of the transition area meet. And then we use this as a criterion for HC2, and we can keep this criterion the same for later research. H star is a vortex melting field where we take the transition slope extrapolate to 0. So here on the figure B, it is the sample at 136 GPa. It is measured in the pulse magnetic field. So although it's in pulse magnetic field, it still has a high data quality. Those curves are not smoothed, and the data quality is quite satisfactory. So then now we can plot phase diagram of different fields against the temperature. Here we use squares to denote HC2, and we use stars to denote H star. For one thing, the upper critical point HC2 of lanthanum at 136 GPa, they agree well with the low field measurement with similar TC. And another thing to notice is this 136 GPa sample has much wide liquid region, vertex liquid region, because it has a history of pressure loss and repressurizing. So I will say the sample homogeneity is not as high, and then it has a wider transition region. Then with all the knowledge of HC2s, we can fit with the WHH fitting, which is normally taken with the study of high temperature superconductors. This equation shows the fitting. It's a summation of infinite series. Small t shows the reduced temperature of reduced by TC, renormalized by TC, and H bar is the HC2 renormalized by TC and the slope of HC2 at TC. Alpha here is a Mackey parameter, and here we approximate the value by the slope of HC2 at TC. So with all those data input into this equation, and this is our fitting of WHH. Still, you can see that relatively small portion of field is available to us, although we already use most powerful non-destructive magnet. So different fittings cannot be quite differentiated with this small amount of field available to us. So we stick to our WHH fitting. With this fitting, we can get HC2 at T equal to 0. And through the relation that psi, the superconducting coherence length, is equal to square root of phi naught over 2 pi HC2, where phi naught is magnetic flux quantum. Once we get the coherence length, we can approximate the Fermi velocity with BCS theory. Although the BCS theory may not hold for this material, but the relation that the psi is proportional to VF over TC would be there. So this is all the data we can get from the quantities we can get from our data, and we can see that the TC differentiate really quite a lot through these two samples. Yet the HC2 are much nearer, and the psi is almost comparable. So with a comparable psi and with a quite different TC, we know that the Fermi velocity for the high TC sample is higher. And this is the key parameters we got for lanthanum H10. We also measured the Hall effect at 120 GPa with the help of that DC magnet. we found that the RxY is linear, the field dependence of the RxY is linear. So which means the transport is dominated by an electron, probably with a single band. And with those leftover few minutes, I also want to show you our recent research about our high field measurement of H2S. The hydrogen sulfur is the first hydrogen superconductor. In this measurement, we measured two samples, one at 160 GPa and one at 155 GPa. In those two samples, we use the same miniature pressure cell, and these two samples actually come from two different cells. For one thing, we noticed that at normal phase, the T dependence is the T dependence of resistivity is proportional to T squared. At this temperature range, we would expect the temperature dependence come from the lattice vibration, and that's usually provide a T linear dependence. So this T squared is actually quite not normal. And examining these two sample, the 155 GPa has a narrower transition and has a higher TC. And 160 GPa sample, on the contrary, it has a lower TC and a wider transition. And that agrees well with the dome, the pressure dependence of TC, the dome it predicts. First, we measure the Hall effect of these two of the 155 GPa sample. We found that for the normal phase, the field dependence of Rxy is quite linear. We think this transport is dominated by a single type of carriers, that's electrons. If we think, if we treat these electrons come from single band, the density of electrons can be calculated with the following relation. And here, we also show the magnetoresistance of H2S. They are both measured in DC and pulse field. And one thing to notice is that the resistance of H2S is much lower than lanthanum H10. While lanthanum H10 would have a few ohms, and those samples would usually have a R of about a few tens of milliohm. Thus, the data here would be expected more noisy. And luckily, you can see that the pulse field and DC field data agrees well with each other. And in this measurement, we use the DC field about 236 Tesla. So which you can notice that at 30, when the thing stopped at 36 Tesla, that was measured in the DC field. We use the same criterion for HC2 and H star, and we found that the vertex liquid region is narrower than lanthanum H10. And then we plot them in a scale of reduced temperature. And we fit those data of HC2 with different models, Ginsburg-Landau, WHH, and strong coupling with lambda equal to 2. So for one thing, we can see that the temperature dependence of HC2 is quite linear through a quite large available field. And with WHH treating, we get a quite small alpha, about 0 to at most 0.3. And we can see that Ginsburg-Landau can rarely fit the data well. They deviate from the data from low field. And WHH is doing a little bit better, but strong coupling fitting did the best job, shown by the blue curve. So with all those data, we know that the superconducting phase is orbital dominated. And also from the data of HC2, we get the coherence length, and all the parameters get is shown in the table. This result has been published recently, and for the audience who are interested, please check for this paper. So here is my summary. So if so Maglab is a user facility for the audience who are interested for magnetic field about tens of Tesla. You are welcome to apply for magnet time at this link. We also designed a pressure cell that's especially suitable for working in the pulse field at low temperatures. We also established key superconducting qualities for hydride superconductors at high magnetic fields. That includes the upper critical fields and the coherence length. The result of the lanthanum H10 is recently placed onto the archive article like this. And so now I'm open for questions. And if you have questions that cannot be raised here, this is my email address. You're welcome to write me an email to ask questions. And thank you for your attention.
Thank you, Dan, for a very clear talk. It was very nice getting all the technical details and hearing about all the different techniques that you use. So questions for Dan. You can just unmute yourself or use the chat box.
I'm just struggling. Did I? Oh, okay. Yeah.
Questions?
Hi, Dan. This is Adam. Thank you for the great talk.
Nice.
On slide 30, you were showing, this plot. So in the 155 gigapascal case, the lower temperatures seem to show some sort of reentrant superconductivity happening at, say, 95 Kelvin. Is this some sort of experimental phenomenon just with inhomogeneous temperatures, or do you think there's physics to be?
So there's so these are the so for the low temperature ones, the transition happens at a higher field. So those are the data from pulse field, and I think the non-zero R measured here is a technical artifact coming from the pulse magnet. So I would say if you want just to get a location of HC2, you can just use this one. And the zeroness of the data, I mean, how to say that, it's not so reliable to get zeroness in a pulse field for superconducting state. I would say, for example, this 111 Kelvin, up to here is all entered into the superconducting phase.
Right. So where on the scale is do you start using the pulsed field again?
30. I mean, this DC field is until 236, and you can notice those are most smooth one. 1, 2, 3, 4. The one of the green ones is still in DC one, and those are more noisy ones. A little bit. So okay. So this 143 and 140, they agree with each other well. But the 143 Kelvin is actually measured in the pulse, and the laters are of course measured in the pulse because our DC field just cannot reach this high.
Right. I was just a little confused because you seem to have non-zero R below 36.
So I just think that in analyzing the pulsate, you have to be more careful because one should have to be more careful than measure things in DC.
Okay, thank you.
Yeah, thanks. There's also a question about slide 29. Go ahead and ask.
Yeah, it looks like slide 29, that leftmost temperature versus resistivity graph, the 155 GPa, the top two, it looks like around maybe, I don't know, 15 milliohms. There's sort of a kink or some kind of feature.
Yes, I think that's it actually have two phases, and actually that's an overlap of two transition here. Yeah.
To superconducting phases?
I would say it's two superconducting phases at a little bit different pressure. So
Okay.
yeah, so it's like a superconducting of two phases, and then this have this kink. Yeah, this sample is quite interesting. For one thing, when we measure in DC, it has a lower pressure, and then after placed into our drawer for 2 months, the TC actually increased. So I guess the sample inside there is slowly reacting during these 2 months too.
Yeah, X-ray diffraction shows that that's very close to a transition structural.
Yeah. I mean, the sharpness shows that it is one, but if it has a slightly different pressure on different regions, so the curve should look like a superposition of two transition curves.
Right.
Thank you.
Thanks. Okay, there's another question.
Yeah.
Hi, thanks for the talk. I have 2 questions about lanthanum hydride.
Yeah.
So the first question is about sample prep. So you showed a sample at 120 GPa. And my question was like, my idea was that the crystal structure is stabilized around 150 GPa. So for the prep, did you increase the pressure to 150, prepare the sample and then reduce the pressure? Or was it possible to synthesize the sample at 120 GPa?
So the sample history is that so in this one we have a list of pressures here. The pressures was at 130 GPa here, and you can see that it originally have a very big resistance, so that we shrink it by 9 to show it into the same plot, and the transition was really sharp. But by the time when it's shipped to our facility, it's unfortunately dropped to 120 GPa. So yeah, as what you inferred, it's actually a kind of uncontrollable decrease of temperature, of pressure. And that's why, and then we increase the pressure step by step until 136 GPa, which is quite near pressure to the one before. And although the ways of transition is a lot larger, but they have a similar TC.
Okay, and I guess like it's not really known how to what the lowest pressures to which the crystal is stable. Like if you decrease it further to 100 GPa, is it known?
We didn't have the chance to go even lower, but I would say at least we have an upper limit for the phase to exist. And also interesting thing to notice that although the 100 GPa sample has much lower TC, still it is high. It's about 200 GPa. So it is still in kind of a high TC phase, but different from what happens here.
Okay, thank you.
That's actually sorry,
Yeah.
that was just a very good point, because the maximum TC is a function of the synthesis pressure. We found that repeatedly, and we've seen TCs below 200 Kelvin as well as above 260 Kelvin. So there's quite a range there, in addition to varying the TC with pressure.
Yeah, I would say to synthesize the sample, one probably need this pressure and temperature combination. But if after the thing formed and if you reduce the pressure, other phases can form, and the boundary is an interesting question to study with.
I see. Thank you. And my second question is about the sort of the nature of superconductivity in LAH10. So I'm taking it, so in terms of predicting the TC for the crystal structure, people use BCS type simulations, but in actuality, the superconductivity is type 2, as you kind of show by vortex lattice sort of postulate that there are 2 critical fields.
Yeah. So as you said, the transition basis is quite wide, and we don't think BCS can describe this system quite well. And so what is the question?
I see. So like basically I'm asking whether kind of it's definitive that it's not a BCS superconductor, but type 2, I guess.
Well, I will say that we are, so the fact that the H star and HC2 is quite far away, it is a fact. And usually for TC this high, it's not BCS. And the coupling is actually quite on the quite high side too. So I will say that's the few hints that's providing for the system.
Okay, thank you very much.
Yep.
Okay, there's a question from Roald. Go ahead, Roald.
Yes, can you hear me?
Yes, hello.
Hi, great work. It's very interesting to see this. I have a question which is in part or mostly to Russ, and but also related to what you do. I'm interested in chemistry, and I also love this whole field just because there is a path dependence in the synthesis, and that's chemistry, so that interests me. So this sample that you're working with, Dan, that was actually synthesized in Hemley's group, is that right?
Actually, no, we get help from the Max Planck in Chemie in Mainz in Germany.
So you got the sample from Germany?
Germany, yes.
Yes. Okay. Now, but then once you got it, you subjected it to additional pressure. Is that right? You had some slides at 130, and then you compressed it to some.
So those ones are the like application for further pressure is also done by the German group.
Yes.
So it's a lot of million back and forth, but yes, they are done by the German group.
Okay.
Yeah.
Now, what I'm interested is how easy to replicate is this synthesis with different methods of getting there. That's what I'm after. And now I know that this comes from the German sample, so I know how it was made there. And it's interesting to compare with this, with what Russ has done. Now, did you do any of the thermal cycling that Hemley and Tozer report in their archive paper?
No, we never went to high temperatures. At most, we get samples from room temperature and cool it down. So I would say we didn't do thermocycling to higher temperatures.
Okay, great. That's what I wanted to know.
Yeah.
And just to add, the experiment that Roald was referring to was an experiment done with ammonia borane as the hydrogen source. So there are additional elements in the system, and we think the TC that's higher in those experiments is connected to the additional boron and nitrogen in the system.
Before the thermalization, their TC is already 290, which is never achievable by the pure lanthanum H10 by either group.
Can I ask, this is Balavi Shivram from Virginia.
Hello.
Hi, thank you for the talk. Shall I say I'm a little bit surprised, particularly the work from Los Alamos, that you didn't, or maybe you, are there any reasons why deuterium is not used? I mean, there has been questions about mechanism of superconductivity, BCS, and so on. One of the key experiments one can do is to replace hydrogen with D2 or
Oh yeah, we did the deuterium research. Yes, we did those. It's just not included into the talk.
What are the results?
The result is they have a lower TC, and they have different temperature dependence of HC2. Yeah, they are not published yet. I don't have a solid conclusion for that, but we did that.
You did that. Okay, very good.
Yeah.
Thank you. On a similar note, before people get excited about exotic metals and so on, although your lanthanum hydride has a linear temperature dependence in the normal state, I do see a slight curvature in the H3S data for in the normal state. So it is not linear.
It is. So we have the deuterium compound of both of them, and yeah, it's not handled yet. But thanks for the interest.
Okay. Last question. The non-metallic high pressure, low temperature cell, have you published the details, or is that available for someone?
I mean, it's I place it onto archive, yes.
So it is on the archive. Okay, thank you.
Yeah, it is through the, it is sent to the publications. If you are interested, this is the archive number.
Okay. Did you ever look at the DuPont material that's called as Vespo? It's a commercial available material. It's extremely high strength at low temperatures.
Just can you repeat? I'm quite interested.
Vespel, V-E-S-P-E-L.
Oh, okay. Yeah, Raspel, I actually use that for the gasket. But I would say that this G10 is just at our hand, and we use it.
Okay,
we call it quite machinable, quite easy to be machinable.
Correct.
And we just use it. But thanks for the recommendation.
Okay, Ronnie Bowler has a question.
Yeah, can you hear me? I hope. Yep. I have a more general question to the broader audience about the formula LAH10. Now, hardened by repetition, or is it real? Or where does this stoichiometry actually come from?
So we did the structure. Yeah, we did the structure measurement. Of course, when you place a sample into X-ray diffraction, only the heavier atoms can be detected. So we mix the location of lanthanum atoms there, and through the calculations, we can make sure of the stoichiometry of the 10 or whether 10 or not. And we found that for both of the pressure, even at 120, which has a quite lower TC, it still have a composition of 1 to 10 here.
But it's also fair to say that we don't know the real stoichiometry, and that's connected to what we think is the variability in TC with synthesis. So it fits experimental systematics for the size of the hydrogens. So it fits LAH10, but we don't have a direct measurement of it in addition to fitting the theoretical prediction.
Yeah.
So only neutrons will tell.
Yeah, I mean, to do different kinds of, yeah, it's, I mean, because we have this high pressure limitation, do all kinds of, so it places a lot of restrictions on different kind of measurement technology. High field like so, neutron like so. So need a, it's not so ready for neutron yet, I would say.
Maybe a second target station at SNS will be able to.
Well, while I'm here, you know, actually, we just had like a couple of weeks ago, we had a really full refinable neutron diffraction at 1.2 megabar at Oak Ridge National Lab. So it is in reach.
And you're on the schedule for the new year, Riney, so we'll hear about that, right?
Actually, I wanted to talk about something else, but I'm not decided yet.
Okay, more questions? If not, thanks very much for a great talk, great discussion.
Yeah, thank you. I feel quite encouraged, and I appreciate this opportunity very well. And yeah, thank you, and have a nice day.
Yes,
Thank you,
thank you.
John.